Welcome. Let's dive right in with our Unit 12 study guide as we look to simplify radical expressions. So, of course, the key detail to remember when we are trying to write a radical in simplest form is that we focus on that factor tree a lot. So, I'm looking at the cube root of 189, and you want to search out for things that you can divide that 189 by. I happen to see that this could be a 3 times 63. 3 is a prime, so I know I can stop on that branch. 63 is not prime, so I would have to think about that. Maybe I'm going to use 9 times 7, where 7 is a prime, so I can stop on that branch. But 9 is not. That's a 3 times 3, and so I keep on going. Now recall, I like to factor all the way until I get my primes, and then focus on your index. My index is 3. That tells me how many items I need to have in a group. So 1, 2, 3 threes appear. That group comes outside of the radical one time. Then inside of the radical, so still inside of that cube root, is any of those leftover primes, and that is the 7. Don't forget to write that index of 3 on there. Then we can move over to number 2 and go ahead to try and make the factor tree for this. So 14 would be a 2 times a 7. Both of those are prime. And 49 would be a 7 times a 7, where both of these are prime. And then I also have to think about those variables. So in that first radical, I have a v to the fourth, 1, 2, 3, 4. And in my second radical, I have a v. So again, I am dealing with cube roots here that were multiplied together. So for those cube roots, I need to find groups of 3. So my 7s are a group of 3. Write that outside once. And for my v's, I can find a group of 3. Write that outside once. Now, anything without that group of 3 gets left inside the radical. Again, don't forget the 3 on your index since we're talking cube roots. There was a 2 that wasn't used, so we can write that inside. And then I've got 2 v's that are left out. They don't have that full match, so we'll have a v squared within. So we're talking 7v times the cube root of 2v squared. Next up, when we look at this number 3, it's an addition problem. Remember, for addition problems, you want to think a little bit about trying to get those like terms. We want to think about getting those like radicals. So I have to simplify each of these. So for 50, I can think about that as a 5 times a 10, where 5 is prime. 10 is a 5 times a 2, where 5 is prime and 2 is prime. So 50 can then be rewritten here as we look. A group of 2, because again, it's a square root, so I have an index of 2. That group of 2 gets written once, and then anything left over stays underneath the radical. I'll do the same process then for my 18. Let's think about this. What can I multiply to make an 18? That could be a 2 times a 9, where 2 is prime, and 9 can be a 3 times a 3, where both 3's are prime. So again, it's a square root. I have an index of 2, so anything that has a match, a pair, gets written outside once. Numbers without a match, like that 2, stay inside the radical. This is still an addition problem, and so we focus on adding those coefficients for us. So I've got a 5 plus a 3, that makes 8, and then the radical stays the same. So we're at 8 times the square root of 2. So when we look at number 4, we will go ahead and make that factor tree for 128. Think about things that can multiply to make that. We could do a 4 times a 32. 4 would have to simplify into a 2 times a 2. Those are prime. 32, we could do 8 times 4. 8 could be a 4 times a 2. And 4 can be multiplied as a 2 times a 2. And this 4 is also not prime. I can do 2 times 2 there. Also then, thinking about my variables, if you want to think about that, m to the 7th means that we are multiplying 1, 2, 3, 4, 5, 6, and 7 of those m's together. So remember that this 4m you had out in front of the radical, that still needs to be in front of the radical. It hasn't gone away. And then you start looking for your groups. It's a square root with no index written, so we're looking for groups of 2. So a group of 2 gets written out front once, a group of 2 gets written out front once, and a group of 2 gets written out front once for my numbers. Also then, for my variables, a group of 2, a group of 2, and a group of 2. Now, to show what's left over under that radical, I have another 2 that didn't get used, and I have an m that didn't get used. So we're going to need to clean all of this up then. We're doing out in front there, the 4 times the 2 times the 2 times the 2. That would give us 32. Then we've got the m times the m times the m times the m. That's putting us at m to the 4th power. And then underneath of that radical, we've got the square root of 2m. So now this number 5, it's another multiplication problem, and we do have values out in front of both of those radicals. You have an option here on that number 5. You could certainly handle this very similarly to what we did in number 2, where you make the factor tree for each individual radical that we are multiplying and then handle it. You could also go ahead and multiply this together to start and then make only one factor tree. That other method would have also worked here in number 2 if we had multiplied to start and then made just one factor tree instead of the 2 factor trees. Either method is going to be good. That's dependent upon your preference there. So as I look at this, number 5, values that are outside of the radicals can multiply with other values outside. So 2 times 8 would make a 16. And then values in the radical can multiply with other values in the radical. So I'm looking at a 7 times a 14 there. That's going to put me with a square root of 98. And my w times w to the 9, of course we know when we multiply those bases, we're going to add the exponents, and so I'm thinking about w to the 10 for that. Now I can go ahead and make my factor tree for what I have under the radical. So I'm going to need to find out what to divide that 98 by. Well, it does happen to be an even number, so we could always do a 2 times 49 to get that. And then 49 would be a 7 times a 7 for us. That's going to work where 7s are prime. And thinking about my variables, w to the 10th, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, if you like to write them out. So whatever I had in front of the radical is going to have to come along for the ride. We haven't lost it. And then we start looking for those matches. So I have a match of 7s to get written once. And I've got a pair of w's to write once, 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 and a match of w's to write once. Anything that's left over stays under the radical, and that's my number 2. Fill it in. Now we go ahead and simplify. So out in front, I've got a 16 times a 7. That is 112. Look at how many w's we are multiplying together here. That is w to the 5th power times the square root of 2. Number 6, notice this is an addition problem. So again, for that addition, we want to start thinking about those like terms. We need the like radicals with it. Now the cube root of 2, this is already pretty well simplified for us. 2 doesn't have any other pieces that we could break that apart into. So when I think about that 16 then, I'm going to think about 2 times 8. 8 would be a 4 times a 2. And 4 is 2 times 2 for us. So I can rewrite that with a cube root. As we're thinking about that, need to have those matches of 3. So a match of 3 gets written once, and anything left without a match stays underneath of that radical. So this is my second term. We're adding this on to that 9 cube root of 2. Notice now both of my terms have cube root of 2 in them. We are ready to add. Focus on the coefficient-like pieces, so that's the 9, and we're adding on 2. That makes 11. Keep that very same cube root of 2 for your final answer. Number 7, here we are going to go ahead and simplify that square root. We're dealing with 108. And so start thinking about a factor tree for that. What is it that we can multiply together to make 108? Well, maybe we will go with a 4 times a 27. 4 is not prime. I could write it as a 2 times 2. 27 is not prime. That can be a 3 times a 9. 3 is a prime, so I can circle it. 9 is not prime, so I'll keep going. 3 times 3 for that. And if you prefer, go ahead and by all means write out your variables if you need to count them. 1, 2, 3, 4, 5, 6 R's, and 1, 2, 3, 4, 5, 6, 7 T's, so that we can look for those matches. So it's a square root looking for groups of 2. A group of 2, 2 gets written once. A group of 2 for the 3's, that gets written once. And when I look at my R's, 1, 2, 3 groups of R's. And then my T's, 1, 2, 3 groups of T's. So anything that's left over stays underneath of the square root under that radical symbol. I've got a 3 that wasn't used, as well as notice we have a t that wasn't used. So now we just have to simplify and put it together. 2 times 3 out in front is going to give us 6. R to the third power, t to the third power, and this is all times the square root of 3t. That's our simplest form. So now in the number 8, we have a multiplication problem. You can choose again for this one if you wish to multiply first and then simplify, or if you wanted to simplify each individually, that's your choice. I think I'm going to go ahead and multiply it first. So my values outside can multiply with other values outside. So that's the 3 times the 5 puts me at a 15. And then for information underneath of the radical, I'm looking at 50 times 6. That puts us at 300. And the x squared times x to the 4th, when you multiply, add those exponents, I get an x to the 6th. So I go ahead and make my factor tree for this then. 300, well, that's going to be a 3 times a 100 for me. 3's prime. 100 I could do as a 10 times 10. And 10 can be a 2 times a 5. 2's prime, 5 prime. And 10 has a 2 times 5 again. 5's prime, 2's prime. And that x to the 6th means that I am multiplying the x times itself 6 times. So any value that I have out in front of that radical has to come along. We can't lose that 15. And I start looking for my groups. It's a square root. So a group of 2 gets written once. A group of 2 for those 2's gets written once. And pair off those x's. A group, and a group. There we are. So now think about what you have left inside that radical. There's this number 3 in the factor tree that we did not use. We have taken care of all of those variables. So we go ahead and multiply what we have out in front. It's a 15 times a 5 times a 2. That makes 150. Our x times x is x to the 3rd, and this is times the square root of 3. Number 9, you can see we have another addition problem, and it's addition and subtraction in this case. Anytime you see that addition or subtraction idea, focus on getting them into those simplest radical forms, because you need to have matching radical forms to be able to add them. So when I think about 20, I'm thinking about a 4 times a 5, and 4 is 2 times 2 in my factor tree. So I can rewrite this with a group of 2's times the square root of 5. Then I look at my square root of 8. Well, 8 would be a 4 times a 2, where 2's prime, and 4 could be 2 times 2. So I find a group of 2's to write it once. A leftover 2 stays underneath of the radical. Remember now, this was a subtraction problem, so I'm going to keep that subtraction sign. I go on to my next term, that's square root of 45. Maybe I'm going to think 9 times 5, where 5's a prime, and 9 would be 3 times 3. 3's are prime. So I find a group of 2, write it down once, and my leftover 5 stays underneath of the radical. Again, that was a subtraction problem. Don't lose your subtraction sign. And lastly then, the square root of 50 needs to be handled. So maybe I think about that as 5 times 10, where 5's a prime. And 10 is 5 times 2, where 5's a prime and 2 is a prime. So I find a match, write it down once. Any values left over without a match, like that 2, stay underneath of the radical. This was an addition problem, so I keep my addition sign. Now notice, you can only add things that have those like radicals. So my 2 square root of 5 can only match up with my negative 3 square root of 5. So 2 minus 3 puts us at negative 1 with the same square root of 5. And then continuing on, our -2 square root of 2 can only match with other square roots of 2's. So I'm thinking about -2 coefficient plus 5 coefficient, and that will give us a +3 times the square root of 2. This is certainly one way to write your answer. If you had done your terms in the other order, and certainly that could have been okay, you might have done 3 square root of 2 minus that 1 square root of 5. That would have also been an acceptable way to represent your answer. So as we flip over to the back and continue on with these practice problems, I've got the square root for 288. So let's find a number that we can divide to start that factor tree. And for 288, maybe I'm thinking about 4 times 72. 4 is a 2 times a 2 for us. And 72 then, let's see, that could be a 4 times an 18. 4 is not prime. I'm going to keep that going for a 2 times a 2. 18 is not prime. I'll do 9 times 2, where 2 is a prime. And that 9 needs to be 3 times 3 so that I can take that all the way to the primes. Again, I focus only on those primes, looking only at these numbers that I have circled. I'm going to go ahead and spell out my variables as well so that I can count them. X to the 6th, write that down 6 times. Y to the 3rd, and Z to the 4th. So I start looking for my matches. It's a square root problem, so matches of 2. A pair of 2's get written once, a pair of 2's gets written once, and a pair of 3's gets written once. Then for my x's, I've got 1, 2, 3 groups of those. For my y's, I can make 1 match, and for my z's, I've got 2 matches in there. Anything without a match is going to stay inside that square root for us. That looks like it's going to cover this number 2 in my factor tree, and that'll also include this y that didn't have a partner. So multiply them together. 2 times 2 times 3 puts us at 12. X to the 3rd, y, z squared, and then under that square root will be a 2y to finish it off. In this 11, you might choose to make your factor tree separately for them, or you could choose to multiply them together and then make just one factor tree. I'm going to go ahead and multiply my square roots. So that 9 times that 4 underneath is a 36, and x squared didn't have anything else to multiply with, y didn't have anything else to multiply with. And you might recognize that your 36 is a perfect square, so you could just recognize square root of 36 is 6. If you don't recognize it, by all means, make yourself a factor tree. 36 is 6 times 6. You can do a 2 times a 3, and your 6 can also be a 2 times a 3. You get all of those primes, and maybe you're going to spell out your x's and spell out your y's for your variables. Look for those matches. So a match of 3's then, right, because I'm looking for pairs, gets written once, and a match of 2's gets written once. I have a match of x's that can get written once outside. Anything that's left over, like that variable y, stays underneath of that radical. Just simplify it. 3 times 2 is a 6. X times the square root of y to finish us off. All right, and so that number 12 then, it's addition and subtraction here. Remember, you got to get these pieces into their simplest forms so that we can look for their like terms and just add them with other of the same radicals. So in my first term, I have a radical that is a square root of 3. 3 is already simplest. In my second term, I have a square root of 3. 3 is already a prime, can't go any simpler. I have a square root of 27. That's going to need to be simplified for us. And so in that third term, I have a square root of 27. 27 is not simplest form, so we are going to need to simplify that radical. 27 could be a 3 times a 9 for us, and 9 would then also have to factor into a 3 times a 3 to find my primes. So in there, I've got a group of 3's to write once and a square root of 3 left over. Remember now that 3 is also being multiplied by that 5a that we have out in front. So this middle term is actually looking at a 15a times the square root of 3 for us. And my last term also has a square root of 3. 3 is already prime, so that is simplest form. So we are talking about then this 13a squared times the square root of 3 minus 2a times the square root of 3 plus that 15 term that we found. And then at the end, we have that minus 4a squared times the square root of 3. So beyond needing to make sure that our radicals match as we add these, we also have to make sure that we have the same variables for those like terms in order to add. So I need an a squared with the square root of 3. That can combine with other a squareds and the square root of 3. So you're thinking 13 minus 4, that would give us 9a squared times the square root of 3. As well as then anything with an a square root of 3 can combine with other a square roots of 3. So I've got a negative 2 and a positive 15 that we are combining. That'll be positive 13a times the square root of 3 to finish us off there. That's as simple as we can go. We don't have any more like terms to add. 13 then wants us to make that factor tree to simplify this cube root. So when I think about 54, I'm going to go ahead and find something to divide this by. I know it's an even, so maybe I'll go with 2 times 27. 2 is a prime. 27 can be a 3 times a 9. 3 is a prime. And 9 would be a 3 times a 3, where those 3's are prime. I'm going to spell out my a's to the 4th. There we go. We've got 4 of them written down. And then b to the 6th. Got them all out. So I look for my matches. I need groups of 3 to go with that 3 index. Every time I find a group, I write it out front once. Every time I find a group of A's, I write it out once. Find a group of B's, write it once. And find a group of B's, I write it once. Anything else that's left is inside the radical. And of course, it's not just a square root. You're writing a cube root with that 3 index. I have a 2 in my factor tree that wasn't included. And I have a letter A in my variables that wasn't included. Now you just got to simplify it and clean up. We're talking 3ab squared times the cube root of 2a to finalize that. Number 14, 2 times the square root there. We're going to make that factor tree for everything under the square root. So 20 is a 4 times a 5. 5's prime. And 4 would be 2 times 2 for us, where those are both prime. And I'm going to write out my x's. I'm going to write out my y's. And I'll write out my z's. 1, 2, 3, 4, 5, 6, 7 of them. So remember, that 2 coefficient that you had in front of the radical, it's still got to be out in front. You can't lose it. And then you start looking for your matches. It's a square root. So I got a match of 2's. I'm going to multiply it out front. Anything else that's a group of 2's, write it out front for the x's. A group of 2 y's and a group of 2 y's, write each group once. I find a match of z's, write it once, a match of z's to write once, and a match of z's to write once. Anything without a match stays inside that radical. So that's going to be my 5 that wasn't used, an x that wasn't used, and a z. Now to simplify it, my 2 times 2 puts us at 4, x, y squared, z to the 3rd. This is times the square root then of 5xz. 15 then wants us to do that square root of 108. So let's make a factor tree for what can we multiply together to make 108. Well, if I do that as a 4 times a 27, then I know 4 is 2 times 2, so I've gotten to primes. 27 can be 3 times 9, where 3 is a prime. 9 is 3 times 3, got that. And for my variables, r to the 6th, 1, 2, 3, 4, 5, 6, and t to the 7th, 1, 2, 3, 4, 5, 6, and 7 of them. Look for the matches. It's a square root, so I need my pairs. A match of 2 2's gets written once. A match of 2 3's gets written once. And for my r's, I've got 1, 2, 3 groups of r's to write. I've got 1, 2, 3 groups of t's to write each of them once. And what's left in the square root? There's a 3 in my factor tree, and there's a t in my variables that haven't gotten used yet. So 2 times 3 makes 6, r to the 3rd, t to the third times the square root of 3t is what we are looking at. Now, 16 is asking us to find the perimeter for this whole rectangle. So perimeter is where we're going to add up all of the side lengths. So I'd like to begin by deciding and discovering how much is the length of this figure. I can see that the width is clearly 3 times the square root of 2, but my length, I've got a 5 square root of 2 for part of it, and I've got a 9 square root of 2 for part of it. So to find that length, I need to add these guys together. So square root of 2's are matching, so I just have to add those coefficients. The 5 plus the 9 puts us at 14 times the square root of 2 meters. Now this also means that across the bottom I have the same 14 times the square root of 2 meters, and my width that was 3 square root of 2 on the left is also going to be a matching 3 square root of 2 on the right. So to find the perimeter, we're going to add these all together. That length, 14 square root of 2, plus my width, 3 square root of 2, plus my length, 14 square root of 2, plus my width, 3 square root of 2. We get to add all of these together. So 14 plus 3 makes 17, plus another 14 puts us at 31, and plus another 3 as those coefficients come along gives us 34 times the same old square root of 2, and these units were in meters. 17 then talks about a square with side lengths of 7 square root of 3 feet. So if you picture that square, it's 7 square root of 3 on the left and 7 square root of 3 on the bottom. Same 7 square root of 3 on the right and 7 square root of 3 on the top, because that square has all the side lengths the same. So when you want to find area, remember that your area is multiplying length times width. So I'm going to be taking 7 times the square root of 3 and multiplying it by 7 times the square root of 3. So I can multiply what's outside of the radicals together. That's 7 times 7, and it makes 49. And you can multiply what's under the radicals together to stay as a new under radical number. So that's 3 times 3 makes the square root of 9. I hope you recognize the square root of 9 is a perfect square. That's equal to 3. So you're actually taking that 49 times 3 for this. You're going to come out with 147, and if we're talking about area, that is square units. So in this case, this is square feet. And that number 18 on the study guide to wrap things up. We're going to start out by assuming that our C and D variables are greater than 0. This means that our variables have to be positive. We don't have any negative variables. So I want to figure out which one of these expressions is the same as 6c to the third d times the square root of 10cd. So I could take each of those 4 answer choices and make a factor tree for them, write them all in simplest radical form, find out which one matches what's given in my question. Or I could take it and think about how I have this 6c to the third d times the square root of 10cd. That's my answer. But what did I have to do to get there? So this is actually saying, right, that I had a 6 and I had the letter c 3 times, I had the variable d 1 time, and then my square root with that 10cd. So think about where this was. In that factor tree, with this being a square root, we were looking for matches of 2. We were looking for pairs. So the 6 had to have shown up 2 times. That letter C, each of them that we wrote down here as a group, had to have shown up twice. And that D had to have shown up twice. Along with, then there had to have been a 10 that didn't have a match, and a C that didn't have a match, and a D that didn't have a match. So put these things together. Look at these numbers. So I've got a 6 times a 6 times a 10. That's 360. And then look at your C's. How many do we have? There's 1, 2, 3, 4, 5, 6, and 7 C's. And then check out your D's. There's 1, 2, and 3 D's. Does that match any of our answer choices? Well, it sure does. That's option D. So perhaps you also want to think about working that backwards. I hope you're feeling so much more confident with your simplifying radicals and that you're going to do an awesome job on this upcoming test.